Good morning, student. So, introduction to MEMS from the chapter number 3, review of basic MEMS fabrication. I am Madhuri Mulik, working as assistant professor in Department of Electronics and Telecommunication, Sharad Institute of Technology, College of Engineering. So, good morning, all of you. So, in the last sessions, we have covered the many points from the chapter number 3. So let us take one overview. So we have seen the deposition techniques, then example of deposition, then why is the deposition, so what is the purpose of the deposition, then which are the types of layers used in a MEMS fabrication, then according to the types of the fields, which are the applications. Okay, then we have seen the one MEMS deposition process example, that is micro cantilever sensor. Then we have seen the types of deposition. So all these types we have covered previously: spin on film, thermal oxidation, chemical vapor deposition, physical vapor deposition, and electroplating deposition. So spin on film, thermal oxidation, then thermal oxidation furnace, steps involved in thermal deposition process, CVD, then two types, homogeneous and heterogeneous, then CVD process, then CVD process steps, then which are the types of the CVD, there is APCVD, CVD, APCVD, PECVD, HDPECVD, then plasma enhanced CVD system, then CVD system for microsystem. Then next type we have seen physical vapor deposition. Then in that physical vapor deposition, scrutiny we have seen. Then in a evaporation method of PVD we have seen. Then we have seen the electroplating. Then we have seen oxidation. So types of oxidation: dry oxidation and wet oxidation. So that thermal oxidation we have seen. Then the last time we have started with the etching. So we have seen the types of etching. So wet etching, dry etching. So wet etching already we have seen. Then dry etching, and why there is a what are the limitations of the wet etching, that we have covered in the last session. Also this figure we have seen. So let us start with the today's session with the new point of the chapter number 3, that is plasma etch. So in plasma etch, the chemical enchant is introduced in the gas phase. Okay, so in plasma etch, the chemical enchant is introduced in the gas phase. Okay, so there is no any wet etching chemical is used. Here plasma used as a gas phase, in gas phase. So for etching silicon oxide, that is CF4, so tetrafluoromethane. Okay, etching silicon oxide CF4, that is tetrafluoromethane is used. So the chamber is first evacuated before introducing the gas. Okay, so the chamber is first evacuated before introducing the gas. So radio frequency electrodes are then used to generate the plasma that ionizes the gas. Okay, see here, radio frequency electrodes are used. So first this chamber is evacuated, introducing the gas. This ionized gas, okay, this reactive gas attacks the oxide layer, removing the layer. Okay, so this is plasma field, this is the gas one, and radio frequency electrodes are used that generated to the plasma that ionizes the gas. Okay, then each rate in plasma is nearly equal to 1 to 10 micrometer per hour. Okay, so 1 to 10 micrometer per hour, much smaller than wet etching, Okay, so it more suitable for thin layer. Okay, it is more suitable for thin layer, but it also provides greater thickness control. Okay, but it also provides greater thickness control. So planar plasma etch configuration, the wafers are held on a grounded chuck. Okay, so the wafers are held on a grounded chuck close to the RF electrodes. Okay, close to the radio frequency electrodes. Then reactive gas introduced in the chamber is ionized. Okay, reactive gas introduced in the chamber is ionized, and the ions helps in material removal. Okay, so is ionized and the ions help in material removal. Okay, so what is the process in plasma etch? So here chemical etchant is introduced in types of the gas. So which type of the chemical etchant in a gas phase used? So tetrafluoromethane is used. So first of all, whatever chamber we are going to take, that is evacuated. After the evacuated, then there is a radio frequency electrodes are used to ionize that the plasma gas. Then ionized gas will attack on the oxide layer, removing the layer. Okay, then each rate in the plasma is the 1 to 10 micrometer per hour, much smaller than the wet etching. So it is more suitable for thin layers, but it is also provides greater thickness control. So the planar plasma etch configuration, the vapors are held on a grounded chuck close to the radio frequency electrodes. So reactive gas introduced in the chamber is ionized, and the ions helps in material removal. Okay, so this is nothing but the plasma etch. Then second type is ion beam etching. Okay, second type is the ion beam etching. So first of all, we are going to observe this figure. What we are seeing here. So argon is inlet from the one side and the plasma is from the another side. So heating cathode coil is used and here anode is used. So whatever the plasma region is attracted to here, but they are due to the heat, they are on that the vapor. So the argons is ionized argon atoms because of this plasma region as well as that the heated atom. So let us see once again. Ion beam etching is similar to the ion beam milling process. Okay, so ion beam etching is similar to the ion beam milling process used that is used for transmission electron microscopy. Transmission electron microscopy sample preparation. Okay, transmission electron microscopy sample preparation. So this is a physical process where ionized inert gas ions, usually AR, are used to remove material from the vapor. Okay, so this is a physical process where ionized inert gas ions are used to remove material from the vapor. The process is not selective, but it is highly directional. Okay, so the process is not selective, but it is highly directional. The ion beam etching process is shown in the figure. So just we have discussed that it is the physical process where ionized gas is used to remove that the material from the vapor. So here that the plasma region, from that the argon is becomes ionized argon atom due to that the heated cathode as well as the anode. Okay, so this is the ion beam etching. Then third method is the reactive ion etching. Okay, so the third method is the reactive ion etching. So reactive ion etching combines the plasma and ion beam. Okay, so reactive ion etching combines the plasma and ion beam etching process to achieve both selective and directionality. both to achieve both selectivity and directionality. Okay, so the reactive ion etching combines the plasma and ion beam etching process to achieve both selective and directionality. Okay, so there is an increase in selectivity compared to the plasma etch for SiO2 and Si. The selectivity ratio is 35:1, while for pure plasma etch the ratio is 10:1. Okay, while for pure plasma etch the ratio is 10:1. Okay, so there is an increase in selectivity compared to plasma etch. For SiO2 and Si, the selectivity ratio is 35:1, while for pure plasma etch the ratio is 10:1. So this reduces the thickness requirement on the mask. Okay, so this reduces the thickness requirement on the mask. So dry etch process is also used for resist. So dry etch process is also used for resist stripping after patterning is complete. Okay, so dry etch process is also used for resist stripping after patterning is complete. So this is usually done by plasma etching using oxygen. Okay, so this is usually done by plasma etching using oxygen. Okay. Then next is the etch process for microsystem. So see the first upon observe the figure. So what is in this figure? So layer of micro machined scanning thermal profilometer. Okay. So here resonant shuttles are there. Okay, in actuator, and here the metal interconnection is there. Here temperature sensor is there, and here substrate is there. Okay, so means see here microsystems are three-dimensional device. Okay, we know that the microsystems are three-dimensional devices consisting of several thin layers of material. Okay, consisting of several thin layers of material. So each layer is designed to serve a specific role. See here, each layer is designed to serve a specific role in the system's functionality. Okay, so a layer may be used as part of electronic circuit, that is maybe insulator or conductor, a structural device for a mechanical component, a transducer layer for a sensor, or a sacrificial layer for device such as cantilever, diaphragms or beams. Okay, so why the etching process is very important in a microsystem? Because the microsystem are three-dimensional device consisting of several thin layers of material. Okay, then each layer of that the microsystem is serve a specific role in that the system functionality. So that a layer may be used as a part of electronic circuit. So it may be work as an insulator or conductor, a structural device or a mechanical component, a transducer layer for sensors, or a sacrificial layer for devices such as cantilever, diaphragms or beams. Okay. So here one example we are going to see, that is transistor etching. Okay, so each layer of a transistor is shown here. So the see here, this is the one transistor. So silicon substrate is there. Then doped regions are here, and first oxide layer is placed here. So these are the metal layers for the contact purpose. Okay, contact. So this is the second oxide layer. It is the first oxide layer and this one is the second oxide layer. Okay, and these are the doped region, and this is nothing but the silicon substrate. So this graphic illustrates 5 etched layers. Okay, this graphic illustrates 5 etched layers which make up the construction of a simple transistor. So which make up the construction of simple transistor. So let us see. The first layer is the silicon substrate. So see here, this is the front violet color layer that will act as a silicon substrate. Okay. So in a second layer, insulating oxide is deposited on the substrate and opening are etched for the doped region. Okay, see here, a layer of insulating oxide is deposited. Means one layer is deposited, that is formed another layer on that the substrate, and opening are etched. So see here, the openings are etched for the doped region. For the doped region. Then a polysilicon layer, this is polysilicon layer, is deposited and etched to provide opening for the metal. A polysilicon layer is deposited and then etched to leave just a small portion for the transistor gate. So this one acts as a transistor gate. So second oxide layer, this one, is deposited, okay, and etched to provide opening for the metal contact to doped regions and gate. Okay. So a metal layer is deposited and etched to form the surface contact. Okay, means every layer is having its specific role. So this figure indicating that how that the etching will take place in a microsystem. And here we have seen that the etched layers of a transistor. So in the first layer, the silicon substrate is there. So the formation of that the silicon substrate. Then second layer of a layer of insulating oxide is deposited. Okay, insulating oxide. So this insulating oxide, okay, so this part is deposited on the substrate, and the same time opening are etched for the doped regions. Means here we have to apply the etching. Okay, then over this, means up to this we have formed in the second layer, second stage, and in the third stage this polysilicon layer is again deposited, okay, and etched to provide opening, etched to leave just a small portion of for the here, okay, for the transistor gate. Then after that, after this polysilicon layer, the second oxide layer, see here, the second oxide layer is deposited and again it is etched to provide the opening for the metal contact to the doped region and the gate. Means in this state, here the second oxide layer deposited and etched to provide the opening for the metal contacts. Then a metal layer is, after that the last stage, a metal layer is deposited and etched to form the surface contact. Okay, it is deposited as well as the etched because it only acquire only specific region and it will act as a surface contact. Okay, so this is nothing but the gate, then maybe this is drain and this is the source. So how that the transistor is made up of in a MEMS system. That is nothing but the one of the best example of the etching. So here the transistor etching we have discussed. Okay. So in this session what we have seen, so from that the types of the etching, in a dry etching, plasma etching we have seen, ion beam etching we have seen, create reactive ion etching we have seen. Then what is the exactly etch process, for that the microsystem is seen, and then after that one example we have taken, that is the transistor etching. So you will get got the idea of the etching in a microsystem. Okay. So thank you.